So, you picked up the packet on the way in. Notice that the test is the day before spring break hits. Okay. So we squeeze it in just before there. I did put 2 formative days in and a catch-up MPAW day, so if for whatever reason we end up with a snow day, we can handle it. Okay? So, to start off with, last chapter, we dealt with forces that were in the radial direction. So forces that were in, forces that were out. Normal force, gravity, those types of things. This is what we used for the sum of the forces equals radial forces, which is MA-rad. These forces cause a change in direction. What we're going to look at this chapter is not all forces act in the radial direction. Some might act part in radial, part not. And so we're going to look at forces that are perpendicular to that radial line. Okay? What do these forces do? Okay? So if these forces cause a change in direction of my velocity, these are going to change the magnitude. What that means for me is these are the forces that are going to cause it to rotate faster, rotate slower, or actually start or stop rotating. Okay? The equation for this looks a lot different though. Here it was kind of the base line that we had for Newton's second law. Now we're going to look at Newton's second law in more of a rotational sense. So I have the sum of the torques is equal to the moment of inertia times alpha. So we're getting some new variables. Remember, last chapter I had that whole page of variables that you had to know. Okay? You still need to know them, but we're going to be adding in a few more this chapter. Not nearly as many, but a few more. Okay? So, before we can start talking about how these forces cause angular acceleration, we're going to first need to know what is this I value and what is this torque value. Okay? So we're going to start with torque. We're going to learn about torque first, and then we're going to kind of put this all together to see how do we get things to actually accelerate angularly. All right. So first thing we're going to do is torque. Unfreeze this here. Okay. And restart it. See if that worked. While it restarts. All right. Torque is dependent on 2 things. And the symbol for torque is a tau. Tau is basically you're going to make your pi symbol, but it only has 1 leg. It doesn't have 2. So it's just a 1-legged pi, if you will. And torque is dependent on, yes, that perpendicular force, but there's more to it. Okay? It's also dependent on R. Okay? So I want to clarify these 2 terms, and then we'll talk about some examples of it. So this just means that it's perpendicular to the radius, or to a radial line. So it's perpendicular to a radial line between the axis of rotation and my force. R is the distance from the axis of rotation to where the force acts. So these are the 2 things that make up torque. Now, let's think about some examples of why we need all of this information to explain how something's going to rotate. So let's take this wrench I have here. Now, if I want to cause this bolt to get screwed in or unscrewed from this board, if I just push straight down, is it going to change anything? No. But I'm smart enough, I get a wrench. What if I just pull on the wrench? Like I pull it this way. Is that going to cause it to turn? No. I need to apply a force that is perpendicular to that wrench to get it to turn. Okay. Now, does it matter where I apply that force? Could I apply that force here? Yeah. Could I apply that force out here? Yeah. Both of those work. Now I want you to think about the doors in the front of our building. Okay. Or any big building for that fact. So you're walking toward that door, you're going to leave, so the door is going to open out for you. And it's got a big glass on top, big glass on the bottom. It's nice and symmetrical, and then it's got this big bar that goes right across the front, right? Yep, she's here. As you walk to that door, do you know which way it's going to open? Is it going to open to the right or open to the left? Do you know? No, so what do? Do you just pick one and go for it? Push in the middle? Maybe push with two hands, and whichever hand gives is the hand you're opening with? Okay? But every once in a while, you should try it. Just go confident into a door. Just pick a side and go for it. What's the worst that's going to happen? Yeah, you're going to run into the door because it's not going to open. Can you technically open a door if you push? Let's say the hinges are right here. So here are the hinges. Could I open the door if I pushed here? What would it have to be true about the push I'd have to apply, though? It have to be a big push, right? I have to push hard. I have to have a large force. What if I push over here? Do I have to push as hard? No, I can have a small push. Okay. So, both of these forces caused angular acceleration. They both produced torque. One of them had to be a bigger force because it had a smaller R value to produce the same amount of torque. Okay? Where we push over here, our force needs to be a lot smaller just because we have a bigger radius. That's why when you look at a door that doesn't have this big bar on it, like ours over here, you notice that the door handle is where? Compared to the hinges. Yeah, it's far away from the hinges. Okay. Makes sense. It's going to allow you to open the door the easiest you can. Another one for you, if you ever run into those ones with the bars, like you might not be able to see the hinges, but sometimes there'll be this thing up here. You can look, that usually is on the side with the hinges, so you can kind of go, oh, all right, go for it, all right? Yeah, because there's nothing worse than hitting that hard side, just being confident about it. Unless you're trying to make it funny, I don't know. All right. So this is how we find torque. If there is a force that's not perpendicular, it's like at an angle, what do we have to do you think? Yeah, you have to resolve it into components. So what we're going to do is we're going to try a couple of those, and we're also going to talk about direction of torque here quick. All right. So let's get an example. So I have, let's say, just some sort of bar. It's rotating about this point. In this chapter, I tend to give rotation spots, axis of rotation, as an X. So if I draw an X somewhere, that's the axis of rotation. That's where it's going to rotate around. Okay, that's its pivot point. Okay. So let's say it's at some angle from the ground, and I want to lift it up. All right, so I apply a force up, F. And is that F perpendicular to my radial line? So this is my radial line, yeah? R? Is that perpendicular? Nope. So I got to do a little bit of some thinking here. So which angle's theta for me? The one above or the one below? This one's theta. So that means the F cosine of theta is here. F sine of theta is here. Okay. So I can then find the perpendicular component, F cosine of theta. Why do I not care about F sine of theta when I want to figure out torque? Because if I pull on the wrench, is it going to rotate at all? No. So do I care about that? No, it's not going to produce any torque, so I ignore that component. It's kind of like when we did work. We didn't care about any forces that were perpendicular to the direction of motion. They didn't do any work. So here I can say the torque is going to be F cosine of theta times how far away it is, r. So this is the traditional way to do it. Now there is a sneaky buck trail for you. It works in some situations, pretty nice. So here we go. This is how you do the sneaky one. So you go along the line that the force is acting along. Okay, so you just make a dashed line there. And then you look for the straight line from the axis of rotation to that dashed line so they're perpendicular. Okay. This is what we call a lever arm. Okay. And in my case, my lever arm, looking at my triangle here, is going to be r cosine of theta. And so all I have to do to find my torque is I have to multiply the force, because I can essentially move that force down here. This is, now it doesn't even look like it's acting on the bar, but that's okay. And so the torque here would be F times r cosine theta. Do I get the same thing? Yeah. So I can either find the component of the force that's perpendicular to the object, or I can find this lever arm idea. Okay. So I have to do this dashed line. I have to move the force up and down along that dashed line until I get to one that's perpendicular. You choose which method's best for you. I'm typically going to stick with the find the force component. Every once in a while, the sneaky buck trail is a better choice, but for the most part, that perpendicular component of the force is going to work for you. All right. So, should we try some of these? Talk about this a little more? All right. So we're going to start with a discussion question before I turn you loose on one of these. So when tightening the lug nuts on a car, lug nuts are the ones that hold the tire on. Okay. So they're important. The critical quantity is torque. Why is torque more important than force applied? So discuss that with the person next to you. Figure it out. Hey, Colin, I got a job for you. For the next 3 days, what I need you to do is pull out the SD card, go upstairs, put it on a flash drive, bring it back down, and put it on my computer in ELT each hour so that I can upload it right away.
Okay. Today during ELT, I'm kind of swamped, but I know it's almost like I have other stuff too. But like the next 2 days, I can.
Okay, is there anyone else up there that can do it today, ELT?
Yeah, there'll be a couple people. No, Woody can come down.
We'll just bring it up there with you.
Yeah.
Because you're up there in ELT or no?
Yeah.
Yeah.
I'll just run up there.
Yeah, just bring it and say, hey, do this, guys. Can you do that for me?
Yeah, no problem.
Thank you. I won't even put in a ticket for it.
All right.
We don't want to get Joey involved.
Yeah, Joey doesn't need to be involved.
Under the table kind of stuff here.
Yeah. Tim's just back, but I have a meeting with Jay on Friday, and I checked my attendance afterward, and it was Monday.
All right, so why is torque important? So let's say you go to the auto shop, and the guy says, oh, I only need 100 newtons of force, and he just kind of pushes down on the lug nut. Is that going to be any good? What if he applies 100 newtons lefty-loosey? Is that going to be effective? No. So those two are obvious, right? They're just not, the nut's not even going to tighten on there. Okay, and hopefully they're smarter than that, right? Now, what is important then if I just have everyone use a wrench and say just apply 100 newtons? Why wouldn't that get them all the same tightness? 100 newtons? Well, yeah, I could. Prove it. They make these kind of things. Spring scale. So this only goes up to 20 though. But I could easily just hook that on there and just pull. There. I'm pulling with, just getting a little tighter, I guess. 4 newtons there I got up to. Well, there's not a hole in the end of this wrench. How would you measure torque? You get someone else to do it for you. All right. What if I apply that force? It says 100 newtons, and I apply that force at half the length of the wrench. Am I going to get it as tight as if I applied it at the full length of the wrench? No. So if I go to that auto shop and one guy tightens it using this, chance of my wheel is probably going to fall off, right? Another guy tightens it like this, hey, my wheel's fine. Next guy says, you know what? I'm going to think. I'm going to use a big R. So he puts a pipe on the end of the wrench, and he applies that force. What might they do to that nut then? Break it. Yeah, strip it or break it. Is that good? No, that's not much better. Okay. So the wheel is going to fall off one way or the other unless you apply the correct amount of torque. So torque, it doesn't matter if I go from one wrench to another wrench, as long as I'm applying the right force at a distance that makes that torque, we're good. Okay? Gives you more information. All right. Go to page 323 and do number 2 on page 323. 323, number 2. Number 2. Oh, we forgot one thing. I forgot about direction. How do we define positive and negative direction? So a torque is positive if it's counterclockwise. It's negative if it's clockwise. Same as math class. When you add up angles, you always start at the positive x-axis and rotate this way for angles. So torque has direction. Sarah, I got to sign you up for Thursday. You're in band all week. figure out those torques.
I don't know the wrong answer. Well, I know that I did this
All right, let's check to make sure you got it done. 28 was the answer, negative 28. Well, let's just make sure you got that. So we had two forces producing two different torques. We had 12 newtons at 30 degrees, and we had 8 newtons perpendicular straight down. My axis of rotation was at the end down here. This distance was 2 meters. This distance was 3 meters. So the 12 newtons, we have to find the perpendicular component. So that is going to be this one, 12 sine of 30. So the torque there is going to be 12 sine of 30 times 2. From the axis of rotation to where the force is being applied. The other one is going to be a torque of 8 newtons times how far away it is, 5. Now there's one other thing I have to identify. I have to identify the direction of the torque. So which way is it, positive or negative? So how you can do that is just take your pencil and just hold it at the axis of rotation and pretend you're that force. So for instance, this force is pushing it and it's causing it to rotate which way? Counterclockwise. So that would be a positive torque. The 8 newtons is causing it to rotate clockwise, so it's a negative torque. So this one just has a negative sign on it. So I put this together, so this torque is going to be 12, and the units come out to newtons times meters because you're multiplying a force by a distance. And this torque comes out to be negative 40 newton meters. Put it together to find the net torque, you get negative 28 Newton meters. There you go. That's number 2. All right, so that's how we find individual torques once we get a net torque. If there is a net torque, there's going to be angular acceleration. It's going to start rotating. If it's stopped, it might slow down, speed up if it's already rotating. If the net torque is 0, if I have a balance of torques, that means it's not going to angularly accelerate. And that is the first case we're going to look at after we do these 3 clicker questions. is when this equals 0. So let's move over to those clicker questions here. So we're going to start with clicker question number 1. Happy birthday. Sunday, yesterday, right? All right.
What are you going to do at the end of the year? Just like,
Yeah, I was worried I wasn't going to get my
5,000
candy.
solar? Because of summer birthdays?
You guys have your own canjos at the end of the year.
You can play yourself with the candy.
Yeah, we can play each other all summer long. You'll have your own canjo with you, though.
You can bring it with you to play football. Bring it out.
There's no better way to make friends at college than with a canjo, let me tell you. So which one's going to produce the greatest amount of torque? Correct answer? A is the correct answer. F1 does produce the most amount of torque. Notice here, even though this one was smaller, 8 newtons instead of 12 newtons, it still produced considerably more torque. Because 1, it was perpendicular, and 2, it was far away. So since all these forces are the same magnitude, the one furthest away and perpendicular is going to produce the most amount of torque. How much torque does F2 produce here? 0. All right. All right, let's do another one. Which of the 4 forces shown here produces a torque about O that is positive? If more than one of these would be E. So if you have 2 answers, you choose E. Remember, positive torques are counterclockwise torques. Correct answer? D. You influence the results. That's funny. All right. So, put your pencil on there. If you're at O, which one's going to produce it to rotate counterclockwise? So I press if I'm F1. Oh, that's clockwise. F3, that's clockwise. F4, oh, there's my counterclockwise. So F4 is the only one that rotates it counterclockwise or positive. So you are able to do the first Mastering Physics question. Mastering Physics is due next Monday, is our first Mastering Physics due date. So, all right. So next, we are going to look at the situation when I add up all of my torques and it adds up to 0. So Newton's second law works the same for rotation as it does for linear. So the sum of the forces equals ma, sum of the torques equals I alpha. They're parallel equations. Okay? We're going to look at situations where alpha is 0 and a is 0, when there's no acceleration and no angular acceleration. If we can set that up as those two conditions, the rest of this here follows. Okay? And if we can get one more condition, if we can get the condition that it's not rotating, that even gives us one more step. So let's go to our green sheet now. All right, equilibrium. Equilibrium tells me, or it's because it's equilibrium. So it's an equilibrium problem because the acceleration is 0 and the angular acceleration is 0. And if you think back to when we did first law problems before, we could also say not only is this true, but we could also say that V is constant, the forces are balanced, that kind of stuff. Omega is going to be constant here as well. Now, as long as this is true, this is your therefore column now. Therefore, the sum of the forces equals 0. Therefore, the sum of the torques equals 0. And one more line of because. So there's going to be a third line of because here. You couldn't fit 3 lines in there?
Well, you made it sound like that was only.
Oh, so you made it bigger. I gotcha. So third thing is if it is a V and omega of 0. Okay. This is going to be a special type called static equilibrium. If that is true, basically, you're going to reference this page. Reference page 1. Because this is essentially what your therefore is. And there's no way we're going to want to write all that down in that green space. Okay. This is that stepwise process you're going to have to do. So the first step is you got to draw a free body diagram. So draw your forces. We've done those. Second step is gravity can be drawn as a single force, just mg. And what we'll do is we'll go ahead and we'll draw it right from the center of mass. So, for instance, if I have this pipe, where would you say the center of mass would be? At the center. Yeah, right there at the center. Okay. So we can draw our gravity right there. We're going to choose an axis of rotation. Now, choose an axis of rotation. So if I have something in regular old equilibrium, okay, so for instance, this one has a constant angular velocity. Where is it rotating about? That point right there, yeah? Okay. How about now? Where is it rotating? Where is it rotating about now? Nowhere. It's not rotating about any spot. Okay? And so whenever you end up with a situation where omega is 0, whenever you end up with that static situation, if I have something like this and it's not rotating about this point just the same as it's not rotating about this point. So that means that any point is equally as valid of a rotation point as any other point. So what that means for us is we get to choose our axis of rotation. Now I'm going to walk you through this choice when we do our example problem next here. All right. Next thing you need to do is you just need to make sure you label everything, all your distances, because torques care about location. And then lastly, we got to also remember to include direction. So let's go ahead and try one of these and see how that all works together. So I have a 7-meter long board with a mass of 25 kilograms. It's supported by two supports. The left support is 1 meter from the left end, and the right support is 3 meters from the right end. What is the upward force supplied by both supports? All right. So they're both going to be supporting it. They're both going to be applying an upward force. Just out of curiosity, see how you're... I know I don't like to let you guys use your feelings in here, but which one do you think is supporting more of the weight or applying a bigger force, would you say? 1 or 2? 2, yeah. You guys have some experiences with this. The reason number 2 is supporting more of the weight, an easy way to think about it is the one that's closest to the center of mass is going to be the one supporting the majority of the weight. Okay. So let's go ahead and just prove that, though. Let's go ahead and find what F1 and F2 are and see if F2 is bigger than F1. All right, so the first thing I need to do is draw a free body diagram. So it's 7 meters long. So I'm drawing a free body diagram of the board itself. So the board is being pushed up by one support, F1. It's being pushed up by another support, F2. And lastly, I have gravity, but where did gravity act? Where's gravity act? In the center, right? And it acts down. There's big old gravity. All right. Now, because we're doing torque, we need to identify direction. So for instance, or positions, I should say, this is 1 meter here. This was 3 meters here. But I also want to identify all these smaller segments as well so that I add up to the whole. So I'll note that this was in the center, so 3.5 meters is half of 7. So if this is 1, that makes this segment 2.5 meters. Makes this segment right here 0.5 meters. So I get all of my segments drawn in there. So I have my forces and I have my segments drawn in there. If you don't know where a force is, just leave it off as far as like the segments go. Like let's say I just said, hey, where's a third support? Just draw it over here. Okay? If you don't know where it is, just draw it on there, but don't include it in the segments, okay? Fair enough? All right. Next, we can start to do some equations. So pretty safe to say that this board is in equilibrium. It's not accelerating linearly. It's not accelerating rotationally. It's not even moving or rotating. So we have a static equilibrium situation, which means that not only are the sum of the forces in the x direction equal to 0, but the sum of the forces in the y direction are also equal to 0. Do I have any forces in my x direction? Nope. Do I have any forces in my y direction? Yeah. So I can generate that equation. So I have F1 plus F2 minus mg equals 0. So I generated my first force equation. Now in the past when we solved static equilibrium problems, that's all we needed to do. We just needed 2 force equations. But here I have how many unknowns? 2. Can I solve this with purely forces? No, I can't. I need torque. So I need to set up a torque equation. All right. So in order to set up a torque equation, so I'm going to sum up the torque set equal to 0. I need to choose an axis of rotation. I can choose it anywhere I want. All right. So here's kind of the general way I like to choose one. I like to choose it on the left side if possible. Okay. And I like to choose it at the location of a force that I don't know, an unknown variable. Okay. So The reason I want to choose it on the left side and at an unknown force, the unknown force is far more important than the left side, by the way. I want to choose it at an unknown force, is if I choose it to the left, any force that acts up is going to produce what kind of rotation, positive or negative? Positive. Any force acting down is going to produce negative. So the direction of the force is the same as the direction of the torque. Is that kind of nice? Yes. So if your axis of rotation is to the left, that works out nice. So this would be producing a negative torque and a positive torque. Now the reason you want to pick it at an unknown force is this. So when I go to find the torques for each one, I'm going to multiply the perpendicular component, they're all perpendicular, that's fine, times how far it is from the axis of rotation. So I have F1 times how far it is away from the axis of rotation, plus F2 times how far away it is from the axis of rotation, minus mg. Why is it minus mg? Because mg is producing a negative torque. Now I just need to fill in these values. So for instance, if the x marks the axis of rotation, how far is F1 from the x? From this point right here, how far is it away? 0. How far is F2 away? 3. How far is mg away? 2.5. Now if I choose my axis of rotation at one of my unknowns, what happens to the unknown in my equation? It goes away. And so now I have an equation with just F2. Can I solve this problem? Yes. The mass is 25 kilograms. So I can put in my 25 kilograms, move this to the other side, and then divide the 3 over. So I have F2 is equal to 25 times 9.8 times 2.5. And then I just need to divide that 3 over. Divide by 3. And I get something like 204 newtons. Now I do understand that you can just take that number and just kind of plug it in right here and solve for F1, right? I want to get you guys some practice though. Go ahead and choose your axis of rotation right here and create a torque equation and solve for F1. Okay? So I'm going to say choose your axis of rotation at F2. I want you to generate a torque equation for me and solve for F1. Okay? So identify if those torques are positive or negative. Are they rotating it counterclockwise or clockwise?
Students, please, at this time, check your emails for ELT requests from teachers.
I had to write down that equation you should have got. So you should have had mg times 0.5 minus F1 times 3 equals 0 because F2 is times 0. I don't know if you wrote it in there or not. I don't remember what this one comes out to. $40.8. And yes, F2 was a larger force, the one closer to the axis or closer to the center of mass.